Hi guys. So far we were describing logic gates with truth tables and mathematical logical expressions. And this is for our purposes good enough, but in this video I want to point out that this is just a mathematical model describing something that exists in the real world. And a mathematical model always has certain simplifications that often are not relevant. So that's why we can make the simplifications. It's good enough for what this model can be used. But you should sometimes be aware that the simplifications might be relevant and might be oversimplifications. Now, the simplification in this description of a logic gate with truth tables and equations is the fact that a logic gate in real life actually needs some time to produce its output from its input. And in circuitverse, you to some degree can actually simulate this so-called delay of logic gates. Let's consider this simple logic gate, a NOT gate, where I simply invert the input. And here it seems that instantly the output is generated from the input. If you use here in circuitverse this flags, you can pick up certain signals, for example, the signal from the input and from the output. So let me connect this here with the input and this second flag called F2 with the output. And then you can use this timing diagram to actually see how the state of the input and the state of the output is correlated. Now, when you hit here this magic button auto calibrate and zoom in, you actually see things a bit in more detail. And currently you see that F1 is at a high state. You see here a curve with value 1, and you see here at F2 a curve with value 0. Now if I change here 1 to 0, the following happens. F1 goes from 1 to 0 and F2 from 0 to 1. But you see that there is a gap in between. That's this so-called delay. It takes some time to generate F2 from F1 using this logic gate. Now for us this is often not relevant because we usually just describe things that exist in real life with mathematical models, and we use these models to understand what this things from electrical engineering is actually doing. But let me show you an example where as a mathematician you could do something that is not working in real life. And I'm talking about the D latch. So that's something I already did show you in a previous video. This D-latch can easily be described with a truth table or with a logical equation. And you can describe that if the clock is 0, the stored data is unchanged, even if you change here D. If you set the clock from 0 to 1, then the stored data equals D. If you change the clock back to 0, you can change D again, and you can formulate this or describe this in a very simple logical equation. And this logical equation actually characterizes the behavior of this D latch. Now, assume you would come up with the idea to use this logical description to actually implement the D latch. Then you would come up with something like this here. And this here exactly reflects this characteristic description of this D latch. You can change here D to 1, nothing happens, the stored data is still 0. You hit the clock, the stored data is 1. You set the clock back to 0. You change D, nothing happens, everything works. But now you can do the following. You can insert here a few more NOT gates, actually 2 of them. Then again, mathematically, a mathematical description would be equivalent to what we had before, because 3 NOT gates are mathematically the same as just one NOT gate. But now this circuit will no longer work. If you now change t to 1, hit the clock, it seems now that 1 is stored in this D latch. Now I hit the clock again, set it back to 0, but then you see actually this 1 is not actually stored. The same, by the way, you would experience if you use here the feature of circuit verse, that you increase the delay, let's say from 10, I guess this is 10 nanoseconds, to 100. And of course, then you again can describe mathematically what happens. But let's first see that it's still not working. Mathematically, it means that this NOT gate takes too long to actually have an effect. It's like canceling out the NOT operator in the logical equation, and then of course you have something which is no longer working. So this is something where I want to point out that what we do is not supposed to actually encourage you to implement in a blind way what we describe mathematically. So far we use our math skills to describe what we discover. Let me also show you a different example. I have built here an half adder, something that you already know, a full adder, and from that a 4-bit adder. And in this 4-bit adder, I pick up the signals as 0, 1, 2, 3, the bits computed in the sum. And then I again use this timing diagram. And now to this bit pattern with just ones, I will add a 1. And then I pause this timing diagram. And now you see what actually happens. In this way, how we implemented our 4-bit adder, we first compute the bit with the least significant bit, then the next bit, and so on. And that means if we would look at the result too quickly, then we might see, for example, that the result is, and that's what you would see here, 0, 1, 1, 1. If we would look at a later time, for example at this time here, we would see the result 0, 0, 1, 1. Then we would later see the result 0, 0, 0, 1. That means because of these delays, we really have to wait a certain time to be sure that the complete result in our adder was computed, because the result propagates from right to left. So this is something that usually we do not care. But now assume that we would like to store the result in some D-latch or in some flip-flop. Then we have to make sure that the clock of this flip-flop, which is actually then moving the result into this flip-flop, is not getting hit before the complete result is computed. So when we do combinations of this logic gates, NOT gates, AND gates, OR gates, together with sequential elements like flip-flops, we have to make sure that the timing is correct. We should not hit the clock too soon. We have to make sure that the delays, the time that is required, is already sufficiently large so that the result is completely done.